Welcome. In this video, we're going to take a look at a problem that combines two types of concepts. One is figuring out the rate law based on some experimental data like we see right here. And then we're going to look at matching that rate law with a reaction mechanism. So first, I've got a data set. I want to figure out the rate law for this reaction. Here is my reaction right here. It's 2x plus y makes z. So to figure out the rate law, I can't just look at the overall chemical equation to figure out the rate law. I need to either know the mechanism or be given some experimental data. So looks like we're given some experimental data. So what we're going to do is, let's say we want to figure out the reaction order for X. I want to compare two experiments where the concentration of X changes, but Y stays the same. So if you look at this first and second data set, it looks like X doubles, Y stays the same. So let's number these. Let's number these 1, 2, 3. So if you compare 1 versus 2, when X doubles, what do we notice about the rate? Well, it looks like the rate stays the same. So X appears to be 0 order. Okay, because if you're 0th order, that means whatever you do the concentration, the rate will not change. Cool. All right, so now let's look at Y. So I'm going to erase this here and let's look at Y. So for Y, again, I want to compare something where Y changes, but X stays the same. So if you compare experiments 2 versus 3, it looks like Y, the concentration Y is doubling. And if I compare these two rates, 2.8 versus 1.4, 2.8 is 2 times faster. And just to clarify, what I'm doing here with the math is I'm just taking the larger number and I'm dividing it by the smaller number. That's why I'm figuring out how much bigger it is. So 2.8 times 10 negative 3 divided by 1.4 times 10 negative 3, that's 2 times bigger. If I do the same thing with the concentrations, 0.4 molar divided by 0.2 molar, that's also 2 times bigger. So when I double the concentration, the rate also doubles, and that is consistent with being first order. So my overall, I kind of ran out of space here, and that's comparing experiments 2 versus 3. So my overall rate law is going to be, I'll write it over here, rate is equal to some constant K. X is to the 0th order, and then Y is first order. So the way that we normally write it is if something's to the 0th order, X to the 0 is 1, so we typically just don't write it. And then when something's to the first order, usually we don't write the 1 up there as an exponent. So usually we write it this way, rate equals K times Y. That would be the rate law for this reaction. And once we know the rate law, we can figure out the value of the rate constant K. So I'm going to take this equation that we just found and I'm going to rearrange it to solve for K. So K is rate divided by Y. And then I can choose any of these data sets because the K is a rate constant. It's constant no matter which, even if you change concentration. So we can do the same calculation with trial 1, 2, or 3. We should get the same result. I'm just going to use trial 1 because it's on the top, but the rate is 1.4 times 10 negative third. It's molarity per second. Concentration of Y is 0.2 molar. If you divide this by this, you end up getting 7 times 10 to the negative third. That is the number that you get. And with molarity, notice how there's 1 m on the top and 1 m on the bottom. So those cancel out. So what's left over is 1 over seconds. Or you could write this as s to the minus 1, inverse second. So with units, just look for m's to cancel out. Usually there's going to be 1 molarity on the top and some number of molarities on the bottom. And you just have to look for what's cancels out, what's left over. So this is part 1, is like figuring out the rate law based on data. Part 2 is to figure out which of these mechanisms fits with the rate law. So we've got 3 possible scenarios. So the way I would approach this problem is go through each of these scenarios and I'd write the rate law that matches this scenario, this mechanism. So for number 1, the first step is the slow step, and it involves 1 molecule of X and 1 molecule of Y. So if this were the mechanism, I'd expect the rate law to be kx times y, because the exponents in the rate law are going to match the number of molecules in the slow step. So there's 1x, 1y. We can see right away this does not match our rate law because we expect it to be first order with y and 0th order with x. So it looks like 1 is not the correct choice. I can eliminate that. Let's go on to my second one. My second one, rate is proportional to k times the molecules in our slow step. So that's y and m. Notice m, however, is an intermediate. Okay, so when I see m, I'm going to go back and I'm going to substitute in the two things that made m. So wherever I see m, I'm going to substitute in two x's. You see how two x's combine to make m? So I'm going to substitute in two x's whenever I see an m. And anyways, this isn't right either, okay? Because we want something that matches this rate law right there. Okay, so hopefully this last one works. Okay, this last one, the first step is the slow step. So the rate law is determined by the number of molecules in the slow step. So there is one molecule of y in the slow step. There are no molecules of x in the slow step. So this one does seem to match with our data and our rate law here, because it seems like I've got, one molecule of y, no molecules of x. The other thing I should check for to make sure this is a valid mechanism is to make sure that it does add up to the overall reaction. Remember, this right here is the overall reaction. So let's test that out as well. So if I add these all up, I'll notice the m's cancel out, n's cancel out, and what we've got left is y and two x's make z. And if I scroll up here, y and two x's make z. Cool, that matches my overall stoichiometry of the reaction. So this does seem like a valid mechanism for how this reaction would be occurring in real life.